So in this video we're going to be talking about the Lambert W function, and a very nice way to introduce this function is to consider the following example. So let's say you have two complex numbers, x and y, and the value of y is given, and you are looking for the value of x, so that this condition is satisfied. So you should have x times e to the x equals to y. So in other words, you should solve this equation to x when the value of y is fixed, is given. Now you can obviously rewrite this problem in terms of this notation if you prefer it. So you can write exp of x instead of e to the x. Now just look at a couple of specific examples of how this equation might look like. So you should only see, for example, the first one to get an idea of how this equation looks like. So x times e to the x equals to 10, and we are looking for the value of x. So we are looking for all of the complex numbers which satisfy this condition. Now you can rephrase the very same problem in terms of looking for the inverse of a function. So we are looking for the inverse with respect to function composition, which is denoted by this circle. So our function is fx is equal to x times e to the x, and we are looking for the inverse. And this function maps from C to a subset of C. And it's going to turn out to be the case that the inverse of this function is a multivalued function. So it's not a proper function, it's a multivalued function. And to demonstrate it with a specific example, we can kind of substitute x with these two numbers. So if we substitute x by minus 2.15329, we are getting the same value as in the case of minus 0.35740, and so on and so forth, which means that the inverse of this function will assign at least two complex values to minus 0.25. Hence, it's a multivalued function. Another example of a multivalued function would be the complex square root function. So for instance, let's consider this equation, I squared is equal to minus 1. But on the same manner, minus I squared is equal to minus 1 as well, which means that the multivalued square root, the multivalued complex square root, is going to assign I and minus I to minus 1. Now you can say that you want to make a function out of it, and you pontificate a principal value, and in this case you can restrict the original function, and the restricted one can be inverted so that you obtain a function instead of a multivalued function. Now, if we define the Lambert W function in a fashion that it's the inverse of the function x times e to the x, then we can easily obtain these equations. Now look at the third one, for example. How did we obtain it? Now we looked at the original problem, and we substituted x with wy. So every time when we saw x, we substituted wy. Therefore, we obtained this equation. Now look at the last one. How did we obtain it? Now see, so the last one comes from the consideration that whenever I see y, I can simply write instead x times e to the x because of the first equation. So these two are equal because of the very fundamental problem we are dealing with. Therefore, I simply, instead of y, I have written x times e to the x, obtaining this last equation. And these last two equations kind of point out how the Lambert multivalued function and this f function x times e to the x kind of reverse each other. So the Lambert multivalued function reverses f, and f reverses the Lambert multivalued function. So let's look at a couple of examples of what are the certain specific values of this multivalued function. So 0 times e to the 0 is going to be 0 times 1, which is going to be 0, which means that one of the values which might be potentially assigned to 0 is going to be 0. Now, this second example is 1 times e to the 1 is going to be 1 times e, which is going to be e, which means that the Lambert multivalued function assigns 1 to e. But it doesn't mean that it's the only value the Lambert multivalued function can assign to e. There might be a case that another value appears as well. That's why I'm utilizing this lower index. So these are two more examples. For example, this one, pi I e to the pi I is going to be pi I multiplied by -1 because of the Euler identity, which is going to be minus pi I, which means that the Lambert multivalued function is going to assign pi I to minus pi I. And there is another example in which we substitute 2 pi, and it's going to conclude us that the 2 pi I is a fixed point of the Lambert multivalued function. And there are a couple of more examples too, and one of the most interesting ones is that when we are looking for the W1 value, now what's going to be the value assigned to 1? So it turns out to be the case, and you can kind of very easily verify it by yourself, that this constant 0.5671, if you substitute it to this expression, the y is going to be 1, which means that the Lambert multivalued function assigns 0.5671 to 1. And this constant has a specific name. It's called omega, and if you are interested in a couple of more digits, then it's represented here, and naturally it means that omega times e to the omega is going to be 1. Thank you so much for watching.